Okay, so you've been given a wire of 10 meters length, and then it's cut into two pieces, which you will determine the length of each. And one of those pieces is a square and the other is a circle. Now, where should you make the cut, as in the length of each piece, where the sum of the total areas of the square and the circle is either the maximum or the minimum? Well, we have to find both, but it's the same step. Can you figure out how to do this? Well, let's see now. For an optimization problem, we need to understand the constraints. In this case, I drew them for you. So, the line here represents the wire that is 10 meters long, and I drew a segment here just to show you how it could be cut into two pieces, one being the circle, the other being the square. Now, this is not to scale, so don't take my word for it. This is not how it would look like, but you get the idea. Now, from this, we're concerned about the total area, which represents the sum of both the areas, right? In other words, I'm going to substitute that areas with the standard forms that we put for those. Now, S squared and R squared really do not help us get anywhere closer, right? But there is one thing that we need to identify here about the constraint. That is the length of the wire. And when we talk about length, we're talking about the perimeter. You cannot have an area with length, right? You form a shape with the perimeter using that length. So, what we're going to do is take out a total perimeter. The total perimeter is the perimeter of the circle or the circumference plus the perimeter of the square. And the total perimeter that could be achieved is 10 meters. So 10 equals 2 pi r plus 4s. And would you look at that? We have a way to substitute a variable in here. What we're going to do is take the easier option. Now the easier option I would say is, let's see, if we bring the 2 pi r over here and divide by 4, we get s equals that. Or we could do 10 minus 4s over 2 pi. Honestly, I don't think it should really matter as long as we look at this equation too, and I think I would rather substitute for the s instead of pi r squared. So the other way would be simpler, but I'd just do it this way. 10 minus 2 pi r over 4 equals s. Now I'm going to simplify that to make it 5 minus pi r over 2. Alright, let's substitute in. So we're going to do pi r squared plus s squared, right? So I'm going to do 5 minus pi r squared over 2 squared. Alright, now we could take the derivative. With respect to r. Alright, so what we're going to do is take the derivative of this 2 pi r plus, this is a chain rule if you couldn't tell. That's right, even a parentheses for an equation, or sorry, expression gives us a chain rule, which is a good thing because I don't have to do the factoring and expanding out, so I can leave it in factor form. So I could just do this. And then times negative pi divided by 4. Alright. And we have to set this equal to 0, remember, to get our critical value. Now, once I do this, 0 equals 2 pi r plus 10 minus 2 pi r times negative pi. So I'm going to simplify this just to make this a little more clear. 2 pi r plus... I'm just going to remove this 2 from here and make this 5 minus pi r over 2 times negative pi. So and if I'm not wrong, we need to add subtract the 5. It's 5 pi. Right. So multiply the 2 everywhere, and now I'm going to divide the pi from everywhere. So 0 equals 4r plus pi r minus 5. I'm going to send the 5 this way, and we'll have 4r plus pi r equals 5. And basically, we'll have 5 over 4 plus pi equals r. This is a critical point. Now we have to take the derivative another time because, yes, we have to find whether this is a max or a minimum. Since we were asked to find both, we wouldn't go wrong either way. So, d squared a over dr squared, which is our notation for the second derivative. And I'm going to now take the derivative from this equation, I think. I think that would be much better than taking it from here, because this is slightly simplified. So I'm going to say 2 pi plus, let's see, pi squared r over 2. So that would just be pi squared over 2. And this part gets, becomes 0. So it would just be pi squared over 2. Alright. Now, no matter what r is, this whole equation will evaluate to a positive number, meaning that the critical point would be at a location which is concave up. So we just found a minimum. We just identified a minimum in a concave up curve. So 5 over 4 plus pi equals r gives us a minimum for our area. Is it the absolute minimum? We don't know yet. Now, since we only have one critical point and we couldn't find the max, and we don't know if this is the smallest minimum, there's one more thing we have to do. We have to evaluate. And we have to do that by using our boundaries. So every time you get a critical point, you have to look at the positives, or not the positives or the negatives. That's for the second derivative. But you have to look at the endpoints of the equation, or I should say scenario itself. For example, our scenario states that the length for a circle can be from 0 to 10. So our r can be 0 to whatever we get from our circumference the value for r that we get, the max value for r, right? So what I'm going to do is draw a number line here, and I'm going to call this end r equals 0. The reason we're doing this is because the critical points don't test the endpoints, because the endpoints, even though they're part of the graph, since they don't extend further beyond that, they don't identify as critical points. So we have to test if they could be the absolute minimum or maximum every time. So our critical point would be over here with r equals 5/4 plus pi. And what I'm going to do is find out the largest value r could be. And that's not that hard, because all we have to do is identify that the maximum length for the circle is 10, and 10 has to be 2 pi r. So if you do the math in your head, you do 5/pi, right? 2 pi r, so 5/pi. Now, what do? Well, let's see. We have to find the maximum area. So, since we're given the equation for area, we can just plug these numbers in for area if you're given a calculator. If not, then we could do some stuff like with the derivative and second derivative to see which way the graph is decreasing and increasing. So let's say it's decreasing over here and increasing over here, right? We know this would be a minimum, and this would be the lowest point over here. Now again, we still have to test the points here to see which one's greater, but you get the idea how we could potentially solve this. So let me just grab the calculator and test out each of the points. And as you can see here, a equals 7.96, which is the maximum area when r is maximized, such that the whole thing turns into a circle. So what are we saying here? The best way to maximize the area is if we don't cut the wire and we make the whole 10 meters into one big circle. And that's your answer.